Now to the second part of the question, which is to show that f is bounded and num of f is equal to b minus a. Now let's start with boundedness, right? Whenever I want to prove that an operator is bounded, for example, this one now, we have f here. If you want to prove that f is bounded, how I like to see it is that I want to show that the norm of the operator is less than or equal to something. That's it. I'm trying to show that that norm has an upper bound. And if it has an upper bound, that means it is bounded. Why, like, if I want to apply this to, probably let me give a real life example. If this is our m, this is our upper bound, and this is the operator f, let's just use that as an example. F can only be from this point to this point. Like whenever it gets to where m is, it cannot go beyond that because it is less than or equal to it. So it can only be lower or equal to it. That means that m is acting as a bound, like a bound for it. I don't know if that makes sense, but yeah. So, but how do we tackle that when we see a question like this? Firstly, you take the absolute value of the function that you were given, which is f of x. So taking the absolute value of f of x, and that's going to be the absolute value of what it is defined as. So here we have the absolute value of the interval of the integration of x of t with respect to t between the interval a and b, and we know that that is less than or equal to if I move the absolute value inside. So now I've been able to show that this is less than or equal to this. Now this is where supremum comes to play again. If you've not seen my previous video about supremum, I think you should watch it because it's to make you understand what we're doing here better. So because I know that the norm of x is the supremum of the absolute value of x of t, I can deduce from that. It implies that x of t is less than or equal to norm of x. How am I able to deduce that? This norm is the supremum, which means that this can only be less than this or equal to this. It cannot be more than this. So since I've been able to imply that x of t is less than or equal to norm of x, if I now decide to replace x of t with norm of x in my integration, I know that this is definitely going to be less than or equal to my integration because this was already less than or equal to this, and now this is less than or equal to this, which means that this can only be less than or equal to this. It cannot be greater than or equal to this because I've replaced this with something that is either bigger than it or equal to this. I hope that makes sense. So since I have this norm here now and there's no t inside, I can bring it out as a constant. So I brought out norm of x here, and then my integration is left with just 1 inside. So when you integrate 1 is a constant, integrate it with respect to t, you're going to have t between the interval this. So I think we understand how we got from here to here. So now I've been able to show that absolute value of f of x is less than or equal to norm of x b minus a. Now from here, this already just implies that norm of f is less than or equal to b minus a. In my previous video, I put an explanation about how we got from here to here, so you can watch that just to understand. But normally some people just try to cover the x, like just eliminate everything that has x inside. We know from here that this holds. So since we've been able to show that sum of f is less than or equal to b minus a, we've been able to show that f is bounded, because what we wanted to show is that number of f is less than or equal to something. This m can be anything, it's just the upper bound. So here our upper bound is b minus a, so f is bounded. Now to show the last part, which is to show that number of f is equal to b minus a, what this is telling you to do is basically estimate the norm, but they have already given you what the estimate is. I just wanted to show that that norm is equal to b minus a. So how we approach this is that we take a constant function and we let the constant function be equal to something. In this case, we let the constant function be equal to 1 just to make our work easy for us. So I said, let's take my constant function to be x naught of t and it's equal to 1. I'm going to replace x with x naught wherever I see it, because f of x is equal to this, right? So f of x naught is going to be this. It's going to be this integration here. And since my x naught of t is equal to 1, I can now replace it with 1 here. So this makes me know that f of x naught is equal to b minus a by performing this integration. Now, supremum is going to come again. We know that the norm of this f here is the supremum of this. Norm of this f naught, let me just say, you know what, no need. Norm of f is the supremum of f of x naught when norm of x is equal to 1. So what does this tell us? This tells us that norm of f would always be greater than or equal to this. Here, it told us that this would always be less than or equal to this. Yeah, it's telling us that this will always be greater than or equal to this. And that makes sense because we know that this norm of f here is the highest value that this could be. This can be less than it, but it cannot be greater than it. It can only be equal or less than, which means that this can only be greater than or less than. It cannot be greater than or equal to, rather. It cannot be less than it. So I can now say that norm of f is less than or equal to the absolute value of f of x naught, and from here we have f of x naught to be equal to b minus a, which implies that this norm of f is greater than or equal to b minus a. And since we've been able to show that norm of f is less than, let me tag this 1, this inequality 1, and this inequality 2. So here in inequality 1, we've been able to see that norm of f is less than or equal to b minus a, and in inequality 2, we've been able to show that norm of f is also greater than or equal to b minus a. That just implies that norm of f is equal to b minus a, because if it's less than or equal to, and if it's greater than or equal to, that means it's equal to, because it cannot be greater than or less than at the same time. It can only be equal to at the same time, and that's why we're able to estimate the norm of f and prove that norm of f is equal to b minus a.